Hey y'all, we are Memphis Cam University and we're back for another Calculus Done Wrong lesson where we run calculus before calculus wrongs us. And today we're going to continue our introduction to limit unit by introducing the all-important notion of continuous or continuity. So keep in mind that this video might be a little bit abstract or theoretical. We're not just introducing some sort of method and applying the rules of that method. We are going to be talking about continuous in a lot of different ways. So first off, we're going to define continuous, probably the best way to start. Then we're going to see how continuous allows us to evaluate limits. Then we're going to understand about ways that things are not continuous, because sometimes it's easier to understand a concept by looking at counterexamples. Finally, we're going to deal with piecewise functions and trying to see how to prove that certain functions are continuous, those piecewise functions are continuous at a certain number, or trying to find a constant that allows a certain function that is piecewise to be continuous at a number. So again, a lot of little things about continuous, so it's going to be a little bit of a mishmash of random things, but everything will be dealing with continuous. So let's talk about continuous. First off, let's define it. So what does it mean for a function to be continuous? So let's define continuous, or continuity, the state of being continuous. So a function is continuous if two things are equal. If the limit as x goes to a of f of x equals f of a. So hopefully you watched our previous video. Our previous video was introducing limits for the first time. And what we talked about is the notion of a limit. And remember that what a limit is you look at y values for your function near your x values of, for example, a certain number a. So instead of looking at the exact y value at, for example, the number 2, what you're doing is you're looking at y values around 2, like 1.9, 1.99, or 2.01, or 2.0001. It's values that are really, really close to 2, but not 2 itself. And what we did is we sort of tried to gather a pattern and see if those numbers are approaching a similar number, sort of the same number, and that number was known as the limit. It was nice to sort of graph these functions. So again, what a limit was if we have this and we have this, what we cared about is what y value we were approaching. And we saw that sometimes we had these nasty things called holes, sometimes we had asymptotes, but what we're going to talk about today is the best scenario. The best case scenario by far is if the limit equals the function value itself. So the best case scenario is that what you're going towards, the y values you're approaching from both sides, is actually the y value there. And that's the notion of continuous. So as you can imagine with the English word continuous, basically you're drawing one continuous line. So while this isn't a rigorous definition and it actually doesn't apply to very complicated problems you might see in college, for a high school sort of level or for a basic college level, when you're dealing with pre-calculus or calculus, when you have a graph, if you want to think about continuous, what I like to think about is you don't lift up your pencil. I'm using a marker, of course, but whatever your writing instrument is. So a function is continuous if you don't lift up your pencil as you draw the function at x equals a. If you don't lift up your pencil. Don't lift up pencil. So why is the notion of continuous so important? Well, notice that it will allow us to evaluate a lot of limits very, very easily. For example, we have the limit as x goes to a of f of x. What we're going to be able to do, if a function is continuous, is we're just going to basically just plug in the number and we're going to get a number and that'll be the answer. To find the limit, we're just going to be able to do this guy instead, and this guy is basically algebra. And thankfully, a lot of our functions that we deal with in calculus or in pre-calculus are continuous. For example, polynomials like x cubed plus 2x minus 1, or trig functions like sine of x or cosine of x, exponential functions like e to the x, all of these functions are continuous. We will be dealing, of course, with some functions that are not continuous, for example, 1 over x or tangent of x, things like that in the future, but it will allow us to evaluate limits for a lot of the functions we care about. Keep in mind that again, eventually, towards the end of this video, we are going to be dealing with piecewise functions, and sometimes when you have piecewise functions, that's when you have a function that's not continuous because you're going to have two different pieces. So you're going to have to lift up your pencil when you draw that. So we're going to try to prove that certain piecewise functions are continuous. So when we do that, what we need to do is we need to show that the limit equals the function value. So that's going to be our goal in those questions. But even to find the limit, what we're going to have to do is find two other things that we talked about a little bit in our previous video. We're going to have to find the two one-sided limits. So in the latter half of this video, we're going to have to prove that this limit, the one-sided limit, what is the y values you're getting as you approach a from the left side, that's what this superscript means, equals what you're getting from the right side. So I don't know why I wrote my f of x so small there. So again, when we want to prove that this is equal to this, first we have to verify that this is even a thing, that this exists. And in order to prove that this exists, we're going to show that this number is equal to this number, or make these two numbers equal to each other. So again, continuous is the best case scenario by far. What you're approaching from the left equals what you're approaching from the right, which means what you're approaching from either direction is the same. And then continuous means it equals that function value. So when we do those piecewise functions, we're going to be finding a lot of things, these four quantities, where these two quantities, if they're equal, automatically makes this third quantity equal. And finally, we're going to try to show that that equals the function value. But that's sort of a really abstract sort of scenarios or introduction to continuous. And oftentimes the best way to learn sort of hard math is through examples. So let's just do a few examples before we get there. So let me erase this. So why continuity is great is it allows us to find limits, for example, like this. The limit is x goes to 2 of x squared plus 3, and then something like on the top, I'm not sure, let's do like x squared minus 2x plus 7. So we're going to be able to recognize pretty easily when a function is bad or when a function is not continuous, because weird things happen. And the main weird things that are going to happen is that when we plug in the number, we're going to divide by 0. And of course, dividing by 0 is not allowed. When you don't get that scenario, that's usually when your function is continuous. So why, again, is continuous so great? Because to evaluate this limit, all we're going to do is go back to our Algebra 1 days, and we're just going to basically plug in 2 into this function. Notice that when you plug in 2 into this function, nothing really bad happens, so the function is continuous. If you were to graph this function, and you looked at x equals a with a calculator or just by hand, you'll see that as you graph this function at x equals a, you don't lift at x equals 2, where a is equal to 2, you don't lift up your pencil. So again, in order to evaluate this limit, all we're going to do is plug in the number. So when we plug in the number, it's going to be 4 minus 4 plus 7. Then when you plug in 2 here, it's going to be 4 plus 3. So it looks like we have the nice number of 7 over 7, so this limit is 1. So again, it's easy to evaluate these limits because we're just plugging the number and we just get an answer and we're good to go. So that's why continuous is so powerful, because evaluating limits is basically just an Algebra 1 question as opposed to a pre-calculus or a calculus question. So let's do some with some harder functions. So with harder functions, we have limit as, say, for example, x goes to 0. We have x squared plus 3 on the bottom, and we have 3 e to the x minus 2 sine of x. So what we're going to see also is that when you combine continuous functions, then the either through sums or products or differences, those functions still are continuous. And as long as you don't divide by 0, then the division of two continuous functions is continuous. So e to the x, if you don't know, its graph looks like this, you don't lift up your pencil. Sine of x, its graph looks like this, you don't lift up your pencil. So the combination of them, even when you multiply them by constants, is still going to be continuous. X squared plus 3, that's a parabola. It doesn't have any zeros, so when you divide it by it, this entire quantity is continuous. So why is continuous again so great? To evaluate this limit, all we're going to do is plug in the number. You do want to make sure that your function is continuous, and the next sort of topic that we're going to talk about are reasons why functions might not be continuous, and there's going to be a lot of videos after this dealing with not continuous functions. But when you have the scenario that a function is continuous, it's very easy, you just plug in the number. So let's try to evaluate this limit. So what we're going to do is we're going to plug in the number. We're going to get 3 e to the 0 minus 2 times sine of 0 over 0 squared plus 3. Again, nothing is weird, it's going to happen. So in this case, e to the 0, what's e to the 0? Well, anything to the 0 is 1, so you get 3 minus Sine of 0, we need to draw the unit circle if you need to be reminded of that. We're having the angle 0, which is right here, corresponding to the point 1 comma 0. Sine of 0 is going to be the y coordinate, so you're going to choose the y coordinate, minus 2 times 0 as well, over 3. Looks like we get it again, the answer of 1. This has been coincidence, of course. Your answer is not always going to be 1, but we certainly appreciate it when it is. So again, continuous is a great notion because it allows us to find these limits very, very easily by plugging in the numbers. And the way sort of continuous laws works is the same way that limit laws work. So this notion of limit or these notions of continuous wouldn't be sort of very useful if it didn't sort of abide by certain laws. So as you're evaluating limits and as you're evaluating continuous functions, you can sort of make assumptions that sort of are logically correct, and while you might not prove that they are rigorously correct, they are basically correct. So for example, the limit of a function, the sum of two functions is the sum of the limit of the functions individually. Same thing here. The limit of 3e to the x minus 2 sine of x is the limit of this one minus the limit of this one, and how we're able to find these limits again is through continuous, because the limit of e to the x is just the value of e to the x at that number, because e to the x is continuous. So hopefully that makes sense. Again, continuous allows us to evaluate these limits when you have continuous functions just by plugging in the number. So now what we need to do is we need to talk about why certain functions are not continuous, and we're going to ascribe certain vocabulary terms in order to sort of separate them into certain types, because sometimes it's easier to understand a math notion when you're dealing with counterexamples. So let's get started with that. So the following are 3 reasons why you might be discontinuous, meaning not continuous. So discontinuity examples. So there's 3 main examples that we're going to be talking about. The first one is going to be called removable. These are going to be mainly your holes that we've been dealing with maybe since algebra 2. The second one is called infinite discontinuity. This is going to be your vertical asymptotes. And then finally, the third one is going to be called jump discontinuity, which is usually your piecewise functions. Jump discontinuity. Usually dealing with piecewise functions that are not continuous. So let's get started. What I'm going to do for each of those is provide one example for each of them. So let me erase this. So the first one, which is the most common one, is going to be removable discontinuity. Again, in layman terms, I don't know why we use these fancy words, removable discontinuity. What my students call them are holes, because they're holes. So they're holes for functions. So the most common example is probably something like this. X squared minus 9 over x minus 3. So let's try to think about this function right here. Well, if you take the function and you graph it, there's only going to be one problem point. So for example, if you plug in something like 2, that's not going to be a problem point. If you wanted to find the limit as x goes to 2 of this function f of x, well, it's the same thing as we did in the previous 2 examples, because when you plug in 2, nothing bad happens. The function is continuous at 2. So to find the limit, all you would do is plug in 2, you get 4 minus 9 on the top, which is negative 5, you get negative 1 on the bottom, so the answer would be 5. But there is certainly one problematic point, and hopefully you can spot it. It's what makes the denominator 0, because if you plug in that number, we can't use the same strategy because you're dividing by 0, and when you divide by 0, the entire world explodes. So when you plug in 3, for example, notice you'll get 0 over 0, so that's why this function is not continuous at x equals 3. So let me try to provide you with a graph of this function so that it's more obvious. This function is actually the same thing as the line x plus 3. So let's try to draw the line x plus 3. 1, 2, 3, and then up 1, up 1, up 1. So x plus 3 right here. So it's this line right here, except that at the point x is equal to 3, there's a hole. And that's basically your function. So you certainly can find the limit. The limit is going to be this y value 6, because notice what you're going towards is this y value 6. So the limit actually exists. The limit of this function from both sides, either the left side or the right side, is the number 6. But remember that continuous doesn't just mean that the limit exists, because the limit exists just tells you that you're approaching a certain number. The limit, what continuity also requires is that the limit equals the function value. So while the limit does exist, which is this point x, the y value 6, the function is not continuous because what you're going towards is not what's actually there. What's actually there is a hole. If we were able to fill in the hole or remove the hole, then the function would be continuous if we were able to fill it in. So that's why it's actually called a removable discontinuity, because we can easily remove it by filling in this hole. But again, this function is not continuous, even if this function does have a limit, because what you're going towards is not what's actually there. The limit does not equal the function value because the function value doesn't exist. If somehow the function value did exist and it was like this would still be not continuous, because as you draw this, you lift up your pencil in order to draw the hole and draw this closed dot. So this is what it means for a function to not be continuous in terms of holes. So let's do the next main example. The next main example is vertical asymptotes. So we have vertical asymptotes. This is going to be called an infinite discontinuity because you're going towards infinity or negative infinity on either side of the vertical asymptote. So infinite discontinuity. I don't know, just spell the word infinite though. Infinite discontinuity. So one of our main examples of infinite discontinuity is going to be tangent of x from our trigonometry days. So let's do f of x is equal to tangent of x. So certainly tangent of x is continuous at certain numbers. For example, if you plug in pi over 4, nothing crazy happens. You're just going to get tangent of pi over 4, which is 1. But there's certain numbers where you will get something crazy happen. Because remember that you can write tangent of x as the same thing as sine of x over cosine of x. And again, the main thing we're trying to avoid is dividing by 0, because that's when sort of weird things happen, chaotic things happen. So when cosine of x equals 0, for example at pi over 2, notice that this function is no longer continuous because you won't be able to get a function value. And again, what does it mean for something to be continuous? The limit equals the function value. So let me redraw at least one period of tangent of x so that you remember what it looks like. So if you draw tangent of x, and you plot it right here, pi over 2, negative pi over 2, tangent looks like this. On the other side, it will look like this. On the other side, it will look like this. So notice that as I draw this function, I have to lift up my pencil anytime I draw the vertical asymptotes. So I draw this, I lift up my pencil to get to this function, I lift up my pencil to get to this function. So this function tangent of x is not continuous at negative pi over 2 and pi over 2 because you lift up your pencil. The function value is not going to be the limit value. So that's our second definition, or second reason why a function might not be continuous. Again, look for things where the denominator is equal to 0. Finally, we have certain scenarios where the limit doesn't even exist, so there's no way that a function can be continuous because you need the limit to be equal to the function value, so you need both of them to be the same. So if one of them doesn't even exist, there's no way that it's equal to something else. So that's what is called a jump discontinuity. And again, usually it's found with piecewise functions. So jump discontinuity. Our example here is going to be what is called the sine function, S-I-G-N, not an S-I-N-E, because it tells you the sign of the function, a certain number. It's going to be this function right here. So you might not know what the graph of this function looks like, but all it is it's two horizontal lines. If x is positive, notice that you're going to get 1. So like if x is equal to 7, the absolute value of 7 over 7, that's just 1. So it's going to be this right here. Then if you're negative, you're going to get negative 1. So for example, if you plug in 6, absolute value of negative 6. Absolute value of negative 6 is 6. 6 divided by negative 6 is negative 1. So this is going to be our function here. So this is what is called a jump discontinuity, because if you have this function, you're jumping, look at my little fingers, you're jumping onto the next function. So let's talk about our two ways to define continuity. The less rigorous way was when we were dealing with pictures and we said it's not continuous if you lift up your pencil when you draw it. So notice that as I drew this function, I have to jump to the other function. So there's no, when I do this, I lift up my pencil. I lift up my pencil as I perform the jump. So this function is not continuous. The more precise way to define continuity is that the limit has to equal the function value. But notice that at x is equal to 0, this is where the function is not continuous. At x equals 0, there's no limit here. I'm approaching this number -1 from the left. I'm approaching this number not -1, sorry. I'm approaching the number x equals 0. From here, I'm approaching the y value -1. Over here, I'm approaching the y value 1. These are not the same thing. So because the limit as x goes to -1 of f of x minus equals the limit as x goes to -1 plus f of x, because these things are not equal, that means that the limit doesn't exist. So when you want to prove continuous, you need to show that this number is equal to this number. What you're going towards is what actually is there. But if I don't know why I have -1s, I mean zeros. So I can't even find this number to verify that it's equal to the second one because these two one-sided limits aren't the same. This limit isn't equal to this limit, so there's no way that this equation holds because this quantity doesn't even exist. You can't equal a number that doesn't exist. And again, why doesn't this exist? When I fix my mistakes, notice that it's because the left limit doesn't equal the right limit. You're not approaching at the same number as you go from both sides. You're approaching different numbers, so the limit doesn't exist. There's no way that this function can be continuous. So those are our three main ways of discontinuity. First one is a hole. That's when the limit does exist usually, but you're not going towards the number that's actually there. Then you have an infinite discontinuity. Those are your vertical asymptotes. So your limit probably isn't going to exist. It's probably going to be infinite or negative infinity. Finally, when you have these jump discontinuities, your limit also won't exist. So there's no way you can have continuous functions. But for the rest of the video, what I want to do is I want to practice with these piecewise functions because they appear on the AP exam, for example. And they're also the functions that are the more interesting functions to deal with because there might be discontinuities. If everything was continuous, then the notion of limit wouldn't be that crazy because we would just be plugging in numbers all day, every day. But because some functions are not continuous, what we're going to do is we're going to practice with those mainly. So let's draw some piecewise functions. Or not draw, but at least state and practice with them. So let's deal with this function right here. F of x is equal to x squared plus 1, x minus 4, and then we're going to use the number x going to 2. So again, all we're doing right now is we're practicing with piecewise functions and trying to find limits of them, because in the next example, we're going to try to prove that certain piecewise functions are continuous at what I call the split point. In order to do that, we again need to find the limit because we need to verify that the limit equals the function value. So when we have these piecewise functions, usually each individual piece is continuous. Like x squared plus 1 is a parabola, you don't lift up your pencil. X minus 4 is a line, you don't lift up your pencil. But because we're switching from this function to this function at this point, weird things might be happening. As we go from the parabola to the line, we might be lifting up our pencil, so that's where the problematic point is. So when we draw these piecewise functions, the point we're going to care about the most is what I call the split number or the split point, and that's where the function changes from one function to the other. But again, mainly what we're trying to do is we're trying to find various things. So what I'm going to try to first find is, I'm going to try to find the limit as x goes to our problematic point of f of x. But because I'm dealing with a piecewise function and there's two pieces on each side, as x is less than 0, the left side, it's this parabola. As x is greater than 2, it's this line. What I need to do is I need to first, in order to find this limit, I need to first find the one-sided limits. And what I'm going to do is I'm going to see if they're equal. If they are equal, that's great. That means that this limit will fully exist. It will be that same number. If they don't equal, that's also okay. That means that this one won't exist. So we do have to find this left limit first. So when you're dealing with piecewise functions, all you have to do is choose the right function you're dealing with. So in this case, because we're going from 2 from the left, we're dealing with numbers like 1, 1.9, 1.99, 1.9999. Notice those numbers are all the numbers that are less than 2. 1.9 is less than 2, 1.99 is less than 2. So you do have to choose which function to do, but it should be pretty easy. If you're coming from the left, you're going to be choosing the less than, and if you're coming from the right, you're going to be doing the greater than 1. And again, keep in mind that these limits individually are pretty easy because these functions are continuous, not at the problematic point. So when we find this limit right here, all we're going to do is we're going to plug in 2 into the right function. In this case, we choose the top function because those are the functions that are dealing with x less than 2. So in this case, we're going to just plug in 2. It's going to be 4 plus 1, which is 5. 2 squared plus 1. Then we're going to do the same thing with the right limit. So the limit as x goes to 2 from the right, f of x. Well, when we plug in 2, looks like it's going to be 2 minus 4. That's negative 2. Notice that 5 does not equal negative 2. So the left limit does not equal the right limit. What does that imply about our full limit or our two-sided limit? That means that this limit doesn't exist. So in this case, we have something that is not continuous. This is going to be a jump discontinuity as we jump from this one to this one at this point x equals 2. But again, when we want to find the limit to the bad number, the split number, what we're going to have to do, and also in the next two examples, is we're going to have to do the two one-sided limits just to see if they're the same number. Sometimes they are, sometimes they're not. Sometimes we're forcing them to be the same number. And when you're doing these one-sided limits, they're pretty easy. You just choose the corresponding function that goes with that one-sided limit. So if you're coming from the left, you're going to choose less than. If you're coming from the right, you're going to choose greater than. And all you're going to do to find those limits, because these functions are continuous, not at the problematic point, all you're going to do is just plug in the number. Or these functions are continuous at the problematic point, but when you combine them, they might not be. Finally, we do have to deal with the equal. What does the equal imply? Well, the equal actually deals with f of 2 itself. What is the function value at exactly 2? So we're going to be dealing with this number as well. So f of 2. And then what's f of 2? Well, how are we going to find this in a piecewise function? Well, because it's f of equals 2 exactly, and the equal sign goes with the bottom one, we're going to choose the bottom function. So it's going to be 2 minus 4, which is equal to negative 2. So notice that in this case, the function value, while it doesn't equal the limit because the limit doesn't exist, it does equal the right-sided limit. So what we call about this is, the notion we describe this sort of scenario is that the function is continuous from the right because the right-sided limit does equal the function value. We will focus mainly though on full continuity from the left side and the right side. And again, that means that the limit equals the function value. But for the next two examples, our last two examples, we are going to be trying to find 4 things just like this one. We're going to try to find the limit and we're trying to find the function. Because again, we're trying to compare to see if these numbers are the same. To find the limit though, we need to find the left limit and the right limit. So really you're finding 3 things that will tell you about a 4th thing. You're going to first find these 2 things, the left limit and the right limit. Then that will show whether the limit exists or not. And finally, we're going to find the function value. When we find these left limits and right limits and function values, all we have to do is pick the right function. If you're dealing from the left, you choose the less than. If you're coming from the right, you choose the right greater than. And finally, if you're choosing the function value itself, you're going to choose the equal sign. So let's do another example of this where we're going to try to prove that a function is continuous. So let me erase this. So let's take this function right here. Let's move this curly brace over a little bit. It's going to be e to the x. Let's say 2e to the x minus cosine of x. Then my next function on the bottom is going to be x squared plus 1. Then we're going to change this number right here. Less than or equal to 0, greater than 0. So I believe I have this correct. So what we're going to try to do is prove that f of x is continuous at x is equal to 0. So our scenario here is that we're going to have 2 functions at x equals 0, and potentially they might look something like this. Probably the closed dot is for the one to the left. And if you draw these 2 functions, obviously when you draw this, when you draw these 2 pieces, because it's a piecewise function, this function is not continuous at x equals 0 because you lift up your pencil when you draw this. But potentially, what we want to prove is that while this is two different pieces, they meet at the same number. So what we're going to try to prove is that while this, it's not going to be this scenario where what we're going to try to prove is that they're sort of meet. So it's going to, even if it's two different pieces, I don't know what these functions look like, but it's going to look something like this. I know what the right one looks like, it's the parabola. But we're going to try to prove that what happens is this sort of scenario. While we have two different pieces, at the problematic point, at our split point, they actually meet. And again, to prove that, you need 4 different things, and we're going to try to find these 4 different things. So let's get started. So the first thing is going to be, we're going to need to first find the one-sided limits. So I start off with the one-sided limits. Because my hope is that these two numbers are the same, and if these two numbers are the same, that means a third thing automatically is the same, the one two-sided limits. So if the left limit equals the right limit, that means the full limit exists. So again, we do have a piecewise function, but how do you find these limits? All you have to do is plug it into the correct piece. So because we're on the left side of 0, we're dealing with numbers that are negative, -1, -0.5, -0.1. As we get closer and closer to 0 from the left side, because we're dealing with numbers less than 0, we're going to choose the top function. So it's going to be 2 e to the 0 minus cosine of 0. We're going to quickly evaluate this. E to the 0 is 1, because anything to the 0 is 1. Cosine of 0 is going to be 1 as well, because you're dealing with the point 1, 0 on the unit circle, and you choose the x-coordinate. So this ends up being 1. 2 times 1 minus 1. Now we're going to do the same thing with the right limit, but we're going to choose the other function. Because when we're dealing with the right limit, we're dealing with numbers like 1, 0.5, 0.1. So because we're dealing with numbers greater than 0, we're going to choose this guy right here, 1 plus 1, or 0 plus 1, sorry, 0 squared plus 1. Again, to evaluate these limits, once you choose the right function, because these limits are continuous, all you do is you just plug in the number. So because we chose to do the bottom function, because we're dealing with something from the right, dealing with positive numbers, all we did is we plugged in 0. When you plug in 0, you notice you'll get 1. So this is the great scenario, the best case scenario, because 1 does equal 1. So because 1 does equal 1, that means that we know a third quantity, which is the full limit, or the limit from both sides, that also equals 1, because the left limit equals the right limit is equal to 1. So in this case, from both sides, we're going to the y value 1. So that means that this equals 1. But keep in mind that this is not sufficient in order to prove continuous. A lot of times people think, or a lot of students think, that this suffices to prove that something is continuous because you showed that the left limit equals the right limit. But remember, from the very beginning of the video, it's not just that the limit exists and it's a number. The limit exists and equals a number, but it has to also equal the function value. What you're going towards, it has to be what's actually there. So even if you have this limit being 1, there could be a hole. So what we need to do is verify that there's not a hole. In fact, there is a y value exactly that is equal to this. So we do need to find a fourth quantity, which is f of 0. And again, to choose f of 0 for a piecewise function, you don't look at the less than or the greater than. You look at the equal exactly, because that's how the piecewise function is defined. So it looks like we're going to be on this piece. So it's going to be the same sort of computation, but we're going to plug it into the top thing. 2 times e to the 0 minus cosine of 0. It's still 1 from our left limit. So just keep in mind that to find the left limit and the function value, we use the same number, the same piece of the piecewise function. And that's because in the piecewise function, they were sort of combined. Less than and equal than. Less than dealing with the left limit, equal dealing with the function value, were defined as the same function. But I like to do it again 2 different times, just to show that I know that you need to find all 4 of these things to make sure that the function is continuous. So in this case, we are finally done, because this limit equals this function value. Again, just showing that the limit exists isn't sufficient. If you were to write this as sort of a sentence, a conclusion sentence, you would say the function is continuous at x equals 0 because the limit equals the function value. They're both equal to 1. So that's what continuous is. That's what I'm trying to stress. It's not just the limit. You need to prove that the limit equals the function value. To find the limit, it is true that you find the left limit and the right limit and make sure that those are equal, but then you need to do one more step and actually find the function value and show that that is equal to your 2 one-sided limits. So that's how it goes. So this is a pretty common question, proving that a function is continuous. For our last question, what we're going to do is something very similar, but we're going to have a generic constant called a, and what we're going to do is we're going to try to find a certain a to make a certain piecewise function continuous at a number. So let's do that to conclude the video. So let's take this right here. And we're going to deal with, let's say, ax squared plus 3. We're going to use the simple number 1. And then we're going to have 2x plus a. So this is going to be my thing. Let's say 4a actually. So I think that will work. Yes. So what we're going to do, the instructions of this question is find a such that f of x is continuous at x equals 1. So before we get to the answer, I want to sort of explain what we're trying to do here in terms of a graph. So keep in mind that on this side, we have x is equal to 1, this important number, and on this side it's a parabola, and on this side it's a line. But keep in mind that a is arbitrary. A could be any number you want. It could be 4, it could be 7, it could be 25, whatever you need. So what happens is that this is going to be a parabola. We're going to have a closed dot here because it's the equal sign is on this side. And then we have this thing, which is a line. And what happens is that if you have different values of a, well, this line and this parabola is going to shift up and down. And what we want to do is we want to find the precise number where this function is continuous. And for a function to be continuous, you don't lift over a pencil. So it would mean that these two functions match. So as we change these a's, what happens is that these functions are maybe over here now, and then over here now. And what we want to do is we want to find the precise number where this function equals this line. So it's going to look something like this, equals this line. So they meet at this point. So that's our goal here. And it's going to be really similar to the last question. What we need to do is we need to find those 4 quantities. The left limit, the right limit, that will make sure that the limit exists. And then finally, we're going to find the function value. We're going to set all those things to be equal, and we're going to solve a nice, easy equation. So let's do that. So we're going to find the left limit as x goes to our problematic point or our split point. That's going to be 1. So it's 1 minus. Then we're going to find our right limit. We're going to force these two things to be equal to each other, so that means that the limit will equal to each other. And finally, we're going to find our function value, f of 1. So as long as all 3 of these things are equal to each other, that makes our function continuous. So just like in the previous one, as we're doing 1 from the left, we need to choose a certain function in order to plug in 1, because once we choose the certain function to find the limit, because these functions are continuous just on their individual pieces, all we have to do is plug in a number. So the hard part is just choosing the right function. We're dealing with numbers from the left, so that's going to be our less than number. So it looks like we're going to be choosing the top function. It's going to be a times 1 squared plus 3. So we get the equation a plus 3. Then we have our right limit. Our right limit is going to be the bottom function because you're dealing with numbers greater than 1, 1.1, 1.01, 1.0001. So what we're going to do is we're going to plug in 1 for x. Looks like it's going to be 2 times 1 plus 4a. So you're going to get 2 plus 4a. So what we're going to do right now is we're going to try to solve for a by forcing these two to be equal. Because again, if this limit equals the right limit, that means that the limits will match. So that means you're going to be going towards the same number. You need these two quantities to be equal in order for the function to be continuous. So for the function to be continuous, we're going to set these two things to be equal to find an a. So it's going to be a plus 3 equals 2 plus 4a. So in this case, looks like we're going to get 3 minus 2, which is 1. We're going to bring over the a, 3a. So it looks like the a we want is 1/3. So as we preface this with a graph, what is the significance of a equals 1/3? Well, if a equals 1/3, it means that this parabola, when a is equal to 1/3, so 1/3 x squared plus 3, and the line 2x plus 4 times 1/3, those will meet at x is equal to 1. So that's sort of our answer here. But what we want to do is we still need to find and verify f of 1 because again, we need the limits to equal the function value. So what's f of 1? Well, f of 1 is going to be chosen from the top thing. It's going to be a times 1 squared plus 3. So it's going to be a plus 3. But if these two things are equal to each other, because the function value happens to be the left limit, because you're dealing with less than and equal, and they're combined, if a is equal to 1/3, all three of these things are going to be equal. So let's sort of finish off by writing a sentence why this function is continuous, and that will be the last thing we do in this video. So if a is equal to 1/3, and it has to be 1/3 because a is the number we found, then the limit of x goes to 1 of f of x will equal the function value. If you need to, you can plug in 1/3, it's going to be a 3 1/3. And this is what it means for a function to be continuous. So f is continuous because the limit equals the function value. That's what we started with at the very beginning. The limit is continuous at x equals 3. X equals 1, sorry, I don't know what I'm talking about anymore after this long video. But this is how you deal with piecewise functions. Again, this video has been pretty theoretical, but hopefully you have a general idea of what continuity means. We define continuity really in two ways. The first way was you don't lift your pencil, and the second way, the more rigorous way, the actual definition of continuous, is that the limit as x approaches a is equal to f of a, the function value. What you're going towards is what's actually there. So throughout this video, we did find limits using the definition of continuous because all we had to do is plug in numbers. Then what we did is we talked about reasons why a function might be not continuous. That is your removable discontinuity, holes, infinite discontinuity, vertical asymptotes, and jump discontinuity, usually with piecewise functions. Then we practice with piecewise functions, trying to find one-sided limits so that we can verify if the limit actually exists. And then we also talked about continuous, again, trying to prove that limits are equal to function values in these piecewise functions. And what we saw is that in order to evaluate the one-sided limits or the function value itself, all you had to do is choose the right function, and we just plugged in the number. Of course, all of this is still pretty tricky and pretty abstract. It's not like other sort of lessons in math where you just have a method or you have a rule and you just immediately apply that rule or process or method. It is sort of a pretty abstract concept, but hopefully you'll get a better grasp of continuity after watching this video. If you want more practice though, we perfectly understand. And what we're going to do is we're going to link our normal Girls Teach Calculus video where one of my former students talks about continuity and limit laws as well. And sometimes you need to hear somebody not a teacher explain it to you, and that they explain it better than a teacher. And so what she does in that video is she practices through a worksheet and she evaluates some limits. And the main thing she does in the latter half of this video, her video, is talk about discontinuities like we did, and finally she deals with some piecewise functions. So if you want to have more practice with that, more practice with continuity, what I would do is I would suggest watching that video. But thanks again for watching this video, of course. Hopefully again you have a better understanding of what continuity is. As you can imagine, we're not going to be dealing with a lot of functions that are perfectly continuous at numbers, because again, it wouldn't be very much of a process that we're doing. All we would do is plug in the numbers. So in our later videos, we're going to be dealing with weirder functions, funkier functions when you divide by 0, functions that are not continuous at the number you're going towards, so you might have to do some sort of algebra step. So be on the lookout for that. Hopefully we'll see you there. Thanks again for watching this video though. We certainly appreciate it, and I hope to see you next time. Thanks again.